Today I am going to talk about the third theorem involving straight lines. Now mind you, this is one of the most important theorems in plane geometry, probably second only to the Pythagorean theorem. So let us see what this theorem is talking about. Now this is what the theorem says. If two parallel lines are intersected by a transversal line, then the resulting interior alternate angles are equal, corresponding angles are equal, the sum of internal angles on any given side of the transversal line is 180 degrees. I repeat, if two parallel lines are intersected by a transversal line, then the resulting interior alternate angles are equal. You know that this symbol represents the word angle. Okay, corresponding angles are equal, the sum of internal angles on any given side of the transversal is 180 degrees. Now as you can see, there are two new terms. Now in the previous video we found out what adjacent and vertically opposite angles are. Now we have two new terms here, interior alternate angles and corresponding angles. Now without knowing what these two terms mean, we cannot really understand what this theorem is talking about. So let us see what interior alternate angles are, what corresponding angles are, and what is meant by the internal angles on any given side of the transversal. Okay, so that's what we are going to do now. Now this is the diagram that is related to theorem number 3. You can see that A, B and C, D are parallel lines. This symbol, it means that they are parallel to one another. That means that they are never going to meet one another. Okay, so A, B and C, D are parallel lines which are being intersected by a single line EF, which we call the transversal line. Now EF intersects AB at G and CD at H. As a result, you can see 8 angles are being formed. Let us see what these 8 angles are. One is this angle, angle EGB. The other one is this angle, angle EGA. Then this angle, angle AGH. Angle HGB. We have 4 angles there. Now here at this intersection, angle GHC, CHF, FHD, GHD. Mind you, you can call it GHD or DHG, it doesn't matter, right? So you can see 8 angles, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 angles that are being formed as a result of this transversal intersecting these two parallel lines. Okay, now to make matters simple, I am going to delete this G and H. Okay, now let us assume that the magnitude of this angle is A degrees, magnitude of this angle is B degrees, magnitude of this angle is C degrees, this is D degrees, this is E degrees, F degrees, G degrees and H degrees. Now mind you, I have used lowercase English letters because I am not that familiar with the Greek alphabet. Okay, so what are interior alternate angles? When two parallel lines are intersected by a transversal, two pairs of interior alternate angles will result in. What are these interior alternate angles? These two are one pair and these two are another pair. This is the first pair, this is the second pair, right? So let's say C and H is one pair, C and H, and the second pair is D and E. D and E, they are interior alternate angles. There are two pairs. Okay, these are two pairs. This is for the first pair, this is the second pair. Now what are corresponding angles? Now you can see angle B is between the top side of AB and the left side of EF. Angle E is between the top side of CD and the left side of EF. So B and E, they correspond to each other. Corresponding angle, this is the first pair. B and E, they correspond to each other. C and F, they also correspond to each other. Why? Now C is between the bottom side of AB and the left side of EF. F is between the bottom side of CD and the left side of EF, right? So C and F, they are also corresponding angles. Similarly, A and H, they are corresponding angles, and the fourth pair is D and G. D and G. Okay, so the theorem says when two parallel lines are intersected by a transversal, the resulting interior alternate angles are equal. C must be equal to H, D must be equal to E, and the corresponding angles are also equal. B must be equal to E, C must be equal to F, A must be equal to H, D must be equal to G. Now, the third part of the theorem says the sum of internal angles, these are the internal angles, these are the external angles, on any given side of the transversal must be 180 degrees. So, the theorem says, the third part of the theorem says that C plus E must be 180 degrees and D plus H also must be 180 degrees. Okay, now we must prove these three parts in order to complete the proof. Now we are going to do that. Let's see how we approach solving this problem. Now this is the challenge. We must prove that C is equal to H and D is equal to E. How are we going to do this? We'll consider these two angles, C and H, these two magnitudes actually, right? This is C degrees, this angle is C degrees, this angle is H degrees. So, if there are any two magnitudes, what are the possibilities? There are three possibilities according to one of the axioms that we have studied in that video on axioms, right? What are the three possibilities? There are three possibilities. C can be less than H, H can be less than C, C is equal to H. Other than these three possibilities, can you think of any other possibility? I don't think so, right? This is common sense. This is an accepted fact. This is an axiom. Okay, so these are the only three possibilities, C being less than H, H being less than C, and C being equal to H. Now we are going to see in this case which of this possibility is true. So we'll assume that C being less than H. Okay, C being less than H. We'll assume this is an assumption. Okay, it's an assumption. Now this one axiom, okay, one axiom. This is an assumption that C being less than H. Okay, so what we do is, if this is true, there is another axiom which says if we add the same magnitude to either side of this inequality, it's going to be like this. Let's say we are going to add E. So C plus E is going to be less than H plus E. We have added E to both left and the right side of this inequality. Okay? Now there is an axiom, I think it's axiom number 9 if I remember right, that if this assumption is true, then this is going to be the result. Okay? If C is less than H, then the sum of C and E is going to be less than sum of H and E. Okay? Now what is the sum of H and E? H and E, they are adjacent angles. It's going to be 180 degrees. Right? So C plus E is less than H plus E, which is equal to 180 degrees. This means that C plus E is less than 180 degrees. So far everything seems okay, but then comes the axiom of parallelism. Can you remember the axiom of parallelism? The axiom of parallelism says, if any two lines are intersected by a transversal and if the sum of internal angles on a particular side is less than 180 degrees, let's say this is A and this is B, sum of A and B is less than 180 degrees, these two lines will meet one another if extended far enough on that same side. That is what the axiom of parallelism says. So if this is true, this is going to be true. If this assumption is true, logically you have to accept the fact that the sum of C and E is going to be less than 180. Now what does this mean? This means that according to the axiom of parallelism, if we extend AB to the left of A and CD to the left of C far enough, they are going to meet one another. Is it possible? No. Why? Because our primary assumption is A, B and C, D are parallel. But if we assume that C is less than H, we come to the conclusion it is unavoidable that AB be not parallel to CD. Right? This is what it is. If you assume this, this is going to be the result. Now this is a contradiction. Now our primary assumption is A, B and C, D, they are parallel. Now if we assume that C is less than H, we come up with the conclusion that A, B is not parallel to C, D. It's not possible. It's a contradiction. So this assumption, the first assumption is not correct. Okay? The first assumption is incorrect because it leads to a contradiction. It gives us absurd results. Right? So this is not possible. Now let us consider the second possibility, H being less than C. This is our assumption. If this assumption is true, then if we add D to both sides, H plus D is going to be less than C plus D. This is an axiom. It's an axiom. It's an accepted fact. If this is true, getting this result is unavoidable. Now we know C plus D is 180 degrees thanks to our theorem number 1. So this is equal to 180 degrees, which means that the sum of H and D is less than 180 degrees. So according to the axiom of parallelism, if the sum of H and D is less than 180 degrees, what's going to happen? AB and CD are going to meet one another if extended far enough to the right. Okay? Is this possible? No. Why? Because our primary assumption is AB and CD, they are never going to meet one another. This also has led to a contradiction, an absurd result. This cannot be true. So according to the axiom now, we can say that C must be equal to H, right? But to be on the safe side, let's see if C being equal to H leads to any contradiction. Okay, let us assume that C is equal to H. Okay, so what are we going to do? Let's add D to both sides. C plus D equals H plus D. If this is true, this is unavoidable. Okay, now we know C plus D is 180 degrees, which means H plus D is 180 degrees. If H plus D is 180 degrees, they are not going to meet one another if extended far enough to the right. They are only going to meet one another according to the axiom of parallelism if H plus D is less than 180 degrees, but they are equal to 180 degrees. So they are not going to meet on the right. What if we add E instead of D? Then C plus E is going to be equal to H plus C. Now we know H plus E is 180 degrees. So C plus E is going to be equal to 180 degrees, which means that AB and CD are not going to meet one another if extended far enough to the left, while C plus E is not less than 180 degrees. They are going to meet one another if they are less than 180 degrees, but they are not. They are equal to 180 degrees, so they are not going to meet one another if extended to the left. Okay, so this assumption does not lead to any contradiction. According to the axiom, that is the only possibility. So we have proven that C is equal to H. Okay, C is equal to H. We have proven this part. Now that method of proof is called proof by contradiction. Now mind you, in plane geometry, most of the time, and even in elementary algebra, most of the time we try to prove things using direct proof, method of direct proof, where we try to prove something directly. But as you go into higher mathematics, you will see that this method of proof called proof by contradiction is going to help you a lot. So you must be quite familiar with the logic behind this method of proof called proof by contradiction. Okay, so we have proven that C is equal to H. Rest is simple. Now we are going to prove that D is equal to E. How are we going to do that? We know that C plus D, thanks to our theorem number 1, is 180 degrees, and E plus H is also 180 degrees. Because of this assumption, we know that D is equal to 180 degrees minus C, and E is equal to 180 degrees minus H. D is equal to 180 degrees minus C. E is equal to 180 degrees minus H. We know that C is equal to H. So all we have to do is we have to replace H with C. So D is equal to 180 degrees minus C. E is equal to 180 degrees minus C. Right? Which means that D is equal to E. We have proven the first part of the theorem, that C is equal to H and D is equal to E. Now we are going to prove that the corresponding angles are equal. We know that from theorem number 2 that B is equal to D and A is equal to C. They are vertical opposite angles. B is equal to D, A is equal to C, E is equal to G, F is equal to H. From theorem number 2. Right? Now we have already proven this. This is first part of theorem number 3. Okay? Now we know that here B is equal to D, D is equal to E. So B must be equal to E. It's obvious, right? B is equal to D and D is equal to E. It means that B is equal to E. Okay? If we consider this one, if A is equal to C and C is equal to H, that means A is equal to H. Okay? If E is equal to G and E is equal to D, then D must be equal to G. Okay? If F is equal to H and H is equal to C, F must be equal to C. B is equal to E, C is equal to F, D is equal to G, A is equal to H. They are corresponding angles. This is how we prove that. Okay, using the first part of theorem number 3 and theorem number 2, we have proven the second part of theorem number 3. Right? Now the last part. How are we going to prove that? Now we know that C is equal to H. Okay, C is equal to H. So what if we add D to both sides? C plus D is going to be equal to H plus D. C plus D is what? 180 degrees. Thanks to our first theorem, we can say, because they are adjacent angles, they are 180 degrees. So H plus D is 180 degrees, which means that the sum of internal angles to the right of the transversal is 180 degrees. What if we add E to this? E instead of D. Now we know the sum of H and E is 180 degrees. Why? They are adjacent angles. So the sum of C and E must be 180 degrees. So the sum of internal angles to the left of the transversal is also 180 degrees. That way I have completed the proof. When any two lines are intersected by a transversal, that would result in two pairs of interior alternate angles and four pairs of corresponding angles. If these two lines are parallel, then these interior alternate angles are going to be equal, and the corresponding angles are also going to be equal, and the sum of internal angles on any given side of the transversal is going to be 180 degrees. That is what the theorem basically says. What is a corollary? Now, the corollary of a theorem is the inverse of a theorem. It's the inverse statement. Now, theorem is a statement which can be proven to be true. So, the corollary of the theorem is the inverse of that statement. Think of this example. If a man is an alcoholic, then he consumes at least 1 bottle per day. The inverse of that statement is, if a man consumes at least 1 bottle per day, then he is an alcoholic. That is actually the inverse of that statement. Okay. Now in mathematics, most of the time corollaries of theorems are theorems themselves, which means that the corollary of most theorems are true. They can be proven to be true, but mind you, always it is not the case. There can be a theorem, but its corollary is not true. Okay? When we consider theorem number 3, the corollary is true. Now, the corollary of theorem number 3 is this. Now, you know that when any two lines are intersected by a transversal, that would result in two pairs of interior alternate angles and four pairs of corresponding angles. Now the corollary is this. If any two lines are intersected by a transversal, and if any pair of interior alternate angles are equal, or any pair of corresponding angles are equal, or if the sum of internal angles on any given side is equal to 180 degrees, then these two lines are parallel. I repeat, when any two lines are intersected by a transversal, and if any pair, now I told you there are two pairs, any pair of the resulting interior alternate angles are equal, or, not and, it says or, because that is alone enough. If any interior alternate angles are equal, they are going to be parallel, or if any corresponding pair of angles are equal, if any corresponding angles are equal, they are going to be parallel, or if the sum of internal angles on any given side is equal to 180 degrees, then these two lines are parallel. Now I am not going to prove that the corollary of theorem number 3 is true right now in this video, right? Because we need to know a little bit about triangles before we complete that proof. With that, I come to the end of this video. I hope this was informative. Thank you for watching, and please subscribe to encourage.